So I have modified a little bit this practical exercise guidelines. Yes, so I added recommended parameters which you may start with, and bonus task. So if you happen to be interested in working further on this practical exercise, you may try to actually improve originally obtained decision feedback equalizer performance, right? Also, there is additional uh, point that you need to include in your practical exercise report. So in the process of setting up this equalizer, we will need to determine the convergence of the coefficients of the filter and estimate a cross-correlation function to find what is the delay introduced by this equalizer. Yes, so these pictures are also needed in your report. So with that in mind, let us proceed to the short theoretical introduction. We had some, I believe, short discussion about this during our lectures previously. You may want to rewatch one of the previous lectures. I believe it was on conclusion of linear equalizers, but I am not exactly sure. No, it wasn't here, I believe. It was further. Yes, it was further. Channel equalizers, yes. So MSE equalizers, adaptive equalizers, yes. So these included also mentioned DFE equalizer, and there was available additional material for you to study, which I believe also includes decision feedback equalizer. By the way, this is quite a good literature source, prepared in Finland, I believe, right? Yes, it's finished in a few years ago, yes. So I definitely recommend to consider this also as a literature for you to study. So anyway, we now will want to understand better what exactly is decision feedback equalizer, how it operates, and most importantly, how should we program it in our practical exercise, which is here. We stopped on this point that we didn't even specify any parameters here. By the way, we might just as well now specify these two recommended parameters as the beginning of the parameters we need. There will be certainly some more, sorry, but these two are most important ones, yes, for this filter to actually work. So as you can see from this presentation, yes, this equalizer consists of two filters, yes. So basically we have a feedback, and inside of this feedback we have located additional filter, yes. So basically this filter, the first filter, which is outside of the feedback, is a regular equalizer such as MSE or zero forced equalizer, yes, whichever we may want to use to calculate these coefficients, yes. Now in feedback filter there is additional equalizer that is used to calculate the error, and this error is furthermore used to improve the performance. So this effect of feedback and additional equalizer, although each of these filters is a linear filter, yes, in total the entire system becomes non-linear just because of this feedback. And also a decision-making algorithm is also non-linear operation, yes. So all in all, this is how we achieve non-linearity without necessarily using any kind of trellis diagrams, paths, and so on, as it is done in Viterbi algorithm, yes. And as of such, we will not suffer from the complexity increase because our impulse response becomes longer, or our constellation size increases. Yes, this doesn't really matter much here. Of course, it will affect the decision-making procedure, but the truth is that we will need to make the decision anyway, because this is a procedure of reading the received binary maybe not necessarily binary, but received data. Yes, so either way, at some point we are going to do this decision anyway, so might just as well do it inside of this equalizer. Why not? Yes. So that is the idea. And here you can see two filters. This is feed forward filter, so for short we are going to denote it as FF, and feedback filter, for short we are going to denote this as FB. And these two parameters that have been specified in the practical exercise are actually the orders of these filters, the length of their impulse response, and accordingly we are going to specify them in our main program right now. Yes, so that would be L feed forward, which was, I believe, 21, and L feedback, which is 3. Yes, so I'm actually also going to copy commands here as well for future needs of further students and further teaching this course. And currently, I believe this is about it, what we can do here. Well, actually, we can maybe add a little bit here. Yes, some formatting, yes. But no, we will get there once we make our function. So as you can see here, we need to create a function which calculates and uses the decision feedback. This sorry, I have forgotten how it's called. Decision feedback equalizer. Yes, it's quite a long time I have been working, so some words are missing from my vocabulary now. Anyway, what we need to do now is to implement this logical diagram in a way of a function. Yes, so that means we need to design two of these filters and accordingly basically describe with the code these connections between filters, including the decision-making process. So that's what we are going to do. So for each of these filters there is the impulse response, yes, which is of the highest interest for us. This is actually our unknown parameter that we must find so that intersymbol interference disappears from our received signal. Before we do that, I'd like to point out once more that the feed-forward filter is a regular compensation filter for channel distortions, just as any other type of equalizers we have checked before. Yes, it equalizes amplitude frequency response. Now, the feedback filter has a separate role in all of this. Yes, its idea is that it puts back intersymbol interference into our signal. So basically it acts the same way as our channel. Yes, so we receive the signal, clear it out of distortions, detect this signal, trying to read data, then intentionally again we distort it just exactly the same way as the channel would. And for what, you may ask? Why do we need to do that? Well, the idea is actually quite simple and well, basically interesting, we can say, in a matter of way. Yes, so considering that this equalizer works correctly, yes, it should remove all the intersymbol interference here. So here you should have clear signal, yes, after this equalizer. Now, after making decision and sending this signal again through the channel, once again you should have here distorted signal, yes, which is ideal if everything is working correctly, is going to be the very same signal that this filter has at its input. So I might denote it as Z with a hat. Yes, so that will be so, they will be equal if everything works completely well. However, as you imagine, it will not be the case for the most time, yes, so meaning these will have some difference, and this difference can be used to improve this equalizer so that it knows that it didn't do well enough. Yes, so this is a feedback for this equalizer for it to become better, yes, in a sense. So that is the general idea about this. Also, as you have noticed, the length of this equalizer was just 21. For this equalizer it's even 3, basically the same as our channel impulse response, as if you have noticed, yes, and in total they have around 24, yes, which is not so much. Nonetheless, this is much more efficient than that MSE equalizer with hundreds of taps, which we tried last time in the part 1, yes, and which didn't give us any effect. So you'll see that with a small number of these coefficients we are actually able to achieve quite a big deal. Actually, there exists even a so-called single tap decision feedback equalizer, yes, single tap DFE, which only has a single one coefficient in this feedback, yes, and probably even in the feed forward also either one or a very small number of these coefficients, and it works, and it can actually be a very good equalizer. It's for specific impulse response, of course, yes. So the number of coefficients is not necessarily what we need here, yes. The non-linearity is what plays the highest and most important role here. So these impulse response can be estimated by using different methods. Yes, we can either use some kind of error considering, yes, which is calculated during the process, or we can use any of the pre-existing methods, or we can use MSE equalizer as a base to improve it somehow. Yes, the possibilities are different. However, as I have described, you might get the impression that the impulse response of this filter should actually be the same as of channel. Well, this is actually not exactly true, because what you get here is effect of combination both of channel and feed forward filter. So these two filters, basically, because we can describe channel as a model of a filter, yes, are merged together. So here you have this convolution between the channel filter and feed forward filter, not exactly just channel filter, yes, because this feed forward filter will change what channel normally does, yes. So for that reason you can see that it's actually possible to estimate these feedback equalizer coefficients if you know these and channel, yes, coefficients, which we happen to do, yes. In our practical exercise it's not a problem to reuse whatever variable we have in our program. Now, since we have this option to find the difference of these two, yes, then we can calculate the error, how, well, basically, which will show where exactly our equalizer is not doing things right, yes, and this error can be further used to improve the main filter equalizer, yes, in the feed forward direction. So this error is being calculated as a difference between the equalized and decided detected symbols, so basically symbols here AM and just detected symbols or equalized symbols YM. So that is the difference, yes, minus YM, which is the error of the equalization. And this error accordingly can be used to improve this filter, and we'll do exactly that in our practical exercise today. So Yes, by the way, here are additional literature which I would recommend also checking out. If you click this link, it will open the web page. By the way, it's already open, has been, yes. So here you can find some more information, particularly about what kinds of impulse responses are better to be addressed by this filter. So as you know, in our practical exercise parameters, if we check mostly your impulse responses look somehow like this. The maximum tap is at the beginning and then some smaller taps, yes? Now, however, sometimes the impulse response may have uh, oh, sorry, smaller values before the maximum value, which is here called a cursor, and uh, smaller value after. And these two halves of the impulse response are handled by a different filter. Yes, so this one is by feed forward filter, this one is by the feedback filter. Yes, so here are some more details with some more formulas. If you are interested, I recommend to study. But at once I'd like to point out one very important aspect here is that well, um, here is some kind of a problem, because this works well only considering that this estimate is actually true. But as you know, because of the intersymbol interference and noise mostly as well, yes, we might actually make error here. That is possible outcome, and we actually even try to evaluate the probability of such event for each signal to noise ratio by constructing the BER plots. Yes, so BER plots which look like somehow like these, depending on SNR. So errors do happen, and they actually are affected by signal to noise ratio. So if the error happens here, it will circulate infinitely in this loop. Yes, so once the error has happened, it will always affect next symbols, and each next error is accordingly going to end up, and therefore this equalizer will start to show worse and worse performance because of these errors. So it needs to actually be sure that this is true information, yes, otherwise it will not really work well. So from this we might conclude that actually this equalizer is good for high signal to noise ratio rather than low. Still, some time delays and whatever else can actually affect its performance, so this is something to consider, that for low signal to noise ratio it can even make situation much worse, yes, and whichever is low and high actually depends on the modulation type, on coding scheme you might use, and so on and so on. So finally, as I said, we could have tried and used any existing method for these, then we could have evaluated these impulse response. However, I felt that it might be interesting to try and make the adaptive equalizer, which is changing its filter coefficients as it operates, with the aid of improving, of course, but as I have just shown you, because of noise and errors, the improvement may not happen, it may actually degrade, yes, because of the noise. Still, it's possible to somehow address these issues anyway, yes. So for adaptive equalizer, it's quite important to notice that we usually don't even know the impulse response, as Chan for us is something that we don't really know. Yes, because in previous algorithms, in let's say Viterbi algorithm, yes, which was let's say for example here, yes, we needed to specify this impulse response, otherwise it will not work. For MSE, yes, we also needed to know this impulse response, otherwise nothing is going to happen. We need to know this to calculate the correct filter. For adaptive decision feedback equalizer, we don't need to know this impulse response. However, in that case, we do need to perform a training stage before we are actually starting to use this equalizer. Training means that we send some arbitrarily arbitrary, and what is more important, uh, how we can say, well known, yes, data. So the data that we know what we should receive, how it should look like, yes, some specific training sequence which we are completely aware of how it should look like, then we receive it here with distortions, noise, we try to equalize it, then we get decision here and compare, is it really what we should get, what we were expecting, or are there any difference? If there are any difference, the adaptive algorithm is going to update this coefficients until it will match. Once it matches, we can switch this to the position on decision device and use further our real data to try to improve this process. So that's exactly how we are going to do it today, yes, in the practical exercise. I thought it might be an interesting to conclude this course with something like this. And well, basically this is actually how it is done in mobile phones and any moving objects, because impulse response is not static. Yes, it's going to change. We have discussed that during our Rayleigh fading channel lectures and practical exercises and so on. Yes, this is actually the way to address this problem. Yes, again, here is the link for more information. Yes, especially for MATLAB codes. Well, you do need specifically MATLAB. Octa will not do, and furthermore, you will even need a version at least 2019A. Yes, but if you don't have, it's okay. You still can at least read some information that is here provided. Yes, and so on. So we are going to use a method called least mean square algorithm, which in more details, by the way, you can study here, yes, in this web page where they discuss adaptive methods. Yes, so a design of adaptive, so LMS equalizer, yes, and here you can read more information about optimization method, how it actually works, and so on and so on. We are going to act as a consumers in this aspect and simply implement this method. So this method is actually pretty simple. Yes, nothing is difficult there. So what we have here is our filter equalizer, filters, coefficients, which we then try to improve by adding error, that is that might be, yes, because if error is going to be 0, nothing is going to be changed. Yes, it's going to remain as it is, and that's it. Now, if there is a slight, even a slight error, we are going to update these coefficients a little bit so that hopefully, and not really hopefully, but based on this least mean square method algorithm, actually we are going to get a better result if we choose the correct parameter of the step size. Yes, well, and if the problem actually can be solved by this method as well. Yes, so what matters here the most is that for the feed forward filter we are going to use symbols from the channel. Yes, so history of the symbols from the channel which arrive on the input of the feed-forward filter are going to be used to update the coefficients along with the error of equalizing. Now, for the feedback filter, we are going to repeat the same process. However, as the data, we are going to use the decision of our algorithm. Yes, so basically what has been equalized and detected, yes, and send it here. So basically you can say this is the input of equalizer, this is the output of equalizer, and we are going to use specifically output of equalizer through this feedback. Yes, well, just like any other feedback works, you send the output signal back to the input in some way. Yes, so this is what happens. So these two formulas are actually what we will need to implement now to get the results. So let us then start working, and we'll start by making a new function. So I'm going to name this function as the DFE EQ. Yes. So here, accordingly, I'm going to type that this is a function called dfeq of different input parameters. So we'll add them as we go. In addition, I'm going to make a test scenario which will call this function so that we might set up this filter for my specific impulse response. Yes, so this is going to be a test scenario. So I do have some test script which is something different which we made in part 1, yes. So here I do some clearing. In a function I don't really have to do because the functions have their own local variables which are created only at the moment of calling this function and afterwards are deleted, so no need to clear anything inside the function anyway, yes. So here I do specify my parameters now, which were accordingly the impulse response of the channel, and wait a minute, why didn't it copy? Then the length of the impulse response, I might have a need for it. Then these two parameters for the decision feedback equalizer. So what else I might need? Signal to noise ratio. Well, yes, we are going to simulate it with noise at some point to see how well it works, if it works correctly. At the beginning I'm going to set it to 100 decibel, effectively meaning no noise, yes. So this is decibel, 100 decibel is no noise added. Well, strictly speaking, it's a very weak noise. However, due to computational precision, yes, it's actually going to be lost, yes. So effectively, this isn't a noise, yes. Then we'll need to generate some specific number of symbols. So let's generate information symbols. We are going to use PAM4 modulation type, yes, which is a axis of the quadrature amplitude modulation, y or x axis, yes, and two such PAM modulations form CAM16 modulation, which we have in our case. So again, we are going to split in the real part and imaginary part and process each one separately. Yes, just as we usually do in this practical exercise. So first of all, I need to specify the number of symbols. Let us specify, well, actually this algorithm will work pretty fast, so I can specify power of 5 here right now. In this program, however, because we already have Viterbi and much going on, it's still better to specify something smaller, yes, during the debugging process. So the idea is that by using this test scenario, we are going to write this function, configure it, find the step size that we actually need to find. There is no, well, actually there are some estimates which we may use as a guidelines. However, I found them not really useful because, well, I anyway need to introduce some kind of a ratio or coefficient, which then basically doesn't change anything. I still have to search for that coefficient, yes. So we are going to try different variants, yes. Accordingly, now I can generate, so for PAM4 we have m equal to 4 number of constellation symbols. Then, as we already did multiple times, I'm going to copy the generation and actually even filtering, yes, so this is the clean signal, not clean, but well, basically transmitted signal input of channel, and this is the channel output signal here, right? Channel output signal. So we apply the filter of this impulse response to our data being transmitted. Next, well, right now I don't think we need to worry about any kind of noise, so I believe we can actually start writing our function. So for this function, we are going to definitely need to specify these two parameters. Yes, I suppose. Well, let's start as if yes, so L forward feed and L feedback, yes. Then, of course, we also are going to need the symbols that we are going to transmit. So that's going to be X, right? So symbols, the coefficients of the filter, and we can actually start to do something, yes, in this function. So first of all, what we need to do is to have the delay line of each of these filters. So this is very nice shown in this picture. As you can see, each of these filters has a delay line of L forward feed elements and L feedback elements accordingly. So we need to initialize them as empty arrays consisting of zeros. Yes, so let's call them state ff as zeros lff, and this is going to be a single column, and accordingly similar way state feedback of the length L feedback. So that is our delay line of each filter that we are going to use to calculate this filtering procedure. Yes, so basically these are the symbols which are accumulated, yes, because as you can see from this picture, equalizer input symbols go through this delay line and decision symbols go through this delay line, so they are going to be diverted there. So we in the process of filtering are going to update these states. Furthermore, we need to actually find the equalizer, yes, so HFF, that's what we want to know, which is also going to be zeros except for the central node. So basically we are going to since we are doing some training procedure, yes, we have to set some initial values, yes, so we are going to choose initial values as all the zeros except the central tab, which is going to be 1. Yes, so that is going to be our initial impulse response, which we are then trying to improve. Well, this works well if we don't have any intersymbol interference. Accordingly, our equalizer will do nothing about it. But if there is any intersymbol interference, it will inevitably start to change something here. Yes, so seems to be quite a good starting point. Yes, so for this to do, we actually need to change the central tab, which is exactly in the center at the position that would be 11, right? No, 12. At the position 12, which we need to express through these LFF minus 1. So no, that is position 10. Again, a mistake. Yes, so that will be 21 minus 1 divided by 2, and at this position we are going to set value to 1. As for the feedback filter, it's initialized by zeros only. Zeros feedback. So let's add some comments here as well. Yes, initialize filters memory state and impulse response. Right? So that is the beginning. Now we are actually ready to start working, yes. And how it will operate? Well, basically it is going to circulate the data in a for loop. So we are going to make a for loop, which is not really MATLAB efficient style, but we are actually just studying, yes, so it will be nice, and it also is very intuitively clear how it operates. So we are going to make some for loop for n starting by 1 ending by n. We don't really know what is n, so I'm going to say n is the length of x, the number of data that we need to process. So we are going to process this symbol by symbol. Yes. Again, I'm going to add this line of activity that something is happening. It will be useful in the future. We added this previously. I just copy paste it. And now we are going to implement. So I do have comments already typed, so I will save up some time. Comments are not so important to repeat them, yes. So we implement now filtering for the feed forward filter memory, yes, so for this part. Well, actually we are going to implement them both, because as you can see what happens here, we have this filter, we have this filter, and the results are added up together. So how do we do that? We are going to try and use at least some matrix calculations here. So well, first of all, what happens at the first moment? At the first moment we have x1 entering this memory cell, and everything else is accordingly shifted by one position. So we need to organize this shifting first of all, then we can start calculating the filter, right? So accordingly, state ff starting from 2 to the end is going to copy state ff starting from 1 to n minus 1. Yes, so these symbols are going to be shifted by one position, and in the place of the first symbol, state ff, we are going to actually put in our input signal value at the moment n. Yes, so this way with each passing n, our data is going to fill in this state, yes, symbol by pushing all them further and further, and accordingly it will be our delay line. Now the equalized symbol, yes, the equalized symbol is a combination of two filtered sequences, yes, so filter 1, filter 2. So let us now first of all try and describe this first filter, yes, this one, in the matrix form. So considering that we have states in the form of this memory state ff, yes, state ff, and state ff, as far as I remember, we didn't specify it here, we specified it here, was I am regularly getting confused about what is column, what is row. So this is a column vector, yes, so we need to multiply this by a row vector. So hff, which is also a column vector, so one of them has to be transposed. The first one becomes row multiplied by column is the result of the filtering, yes. So in one go we perform this all procedures, yes. Basically we multiply this by x, this multiplied by whatever was here, this multiplied by whatever was here, and so on and so on, and add everything together. As you know, matrix multiplication, row by column, operates exactly in this manner. So we repeat the same process for the second filter, yes, so that would be plus hfb transposed multiplied by state fb. And all of that is going to produce a single output symbol, which is equalized symbol n. Now, if we leave it as it is, the MATLAB will start to run slower and slower and slower with each iteration. Well, actually, I might even demonstrate this to you. Yes, so let's say this is going to be some y equal to this, and let's say y is initially 0. It doesn't matter, we just want to assign something. Yes, so now I'm going to run this scenario, yes, by calling this function. So as x, I specify xchan. I run this now, and in Octave here the progress happens. So let me increase the number to, let's say, 7 or maybe 6, like, okay, to make it more clear that it becomes slower. Yes, so now you can see that it's working. However, you may notice that it is slightly slowing down with each next step. Yes, right now I don't think I feel that. But the longer this vector is, the slower and slower it becomes. I might even choose 5 maybe. One more. But this is just going to be generally slow, yes? So in order to avoid that, we actually should pre-allocate this array in its full size, yes? So we do some pre-allocate vectors. So that is EQSIM should be filled in with zeros, and there is total number n of these zeros, yes? So if we do it like this, it should start working faster, yes? So let me again run this. So now it shouldn't decrease any speed. Well, actually, maybe even vice versa, it should be more clear if we use something small like this. Oh, sorry, I have run incorrect script. Sorry, I needed test scenario. No, it's difficult to show this on some fast process, yes, but at any rate, if we make multiple of such variables, it's going to start slowing down us. So again, next thing we are going to calculate is going to be error, which is also going to be a vector. So we are going to set this equal to the same zeros. So I could have written zeros y1n, or it's exactly the same as this. Yes, so I just copied these zeros, and finally the y. Yes, what we are interested to get also should be pre-allocated. So also equsim. Yes. So now we have equalize symbol calculated, right? And the next step, according to this diagram, would be to make a decision. Yes, decision, what is this symbol? Let me remind you that for PAM3 we have +3, we have +1, we have -1, we have -3. Yes, so if we were to say that, for example, yn is equal to eqsim n, and let's see what is being produced by this program. Yes, that is y. You will see that we don't see always this 1. Here you can see 7, -3, -4, -2.8, -0.4, and so on. So we need to detect them to be either one of those all symbols. And we cannot really even round them normally. Yes, we do need to actually adjust them to the closest possible value, which is again the same as calculating different metrics. So for example, let us take these -4. Well, no, this is not interesting case. Let us take maybe some more interesting case, which is let's say -2.4. Is it -1 or is it -3? Of course it is -3 because it's closer to -3. However, how can we program that? Yes, so I'm going to show you that we are going to have this multiplied by a column of ones, like this, replicated, and then we subtract all the possible versions, -3, -1, +1, or +3, like this. So here you can see the difference. Yes, what we are interested in is the absolute value of this difference, so or even squared. Yes, because after squaring small number it becomes even smaller. That's a good thing. Yes, so here we had 0.6, now we have 0.36. This number was 1.4, now it's not 1.96. The difference became better, especially that can be seen here. Yes, so that is a good thing to do, to square in this particular case. So now we only need to find out which row is a minimum, and that would be our answer. Yes, because if we know that this is the first row, then we need to read from this map first symbol. That's the idea of how we are going to make this detection for PAM4. Yes. So for this we need to actually well, I'm not going to write it in one long line. Yes, I'm better making some multiple shorter lines so that they are understood better. Yes, so first of all, I'm going to find the distance. I don't really need to store each of these distances for each of the symbols. I need to calculate it as an intermediate variable, which I then can forget about until next symbol. So I not assign any index here. So distance is, as I said, once, yes, with the number of symbols that is we can use m. Yes, m is equal to 4. I don't really want to specify this as a parameter because, as you will see, there will be quite a lot of parameters anyway for this function. We don't need much more. Yes, so once that would be m1 multiplied by the equalized symbol n minus map of the possible symbols. So here actually we need to do it like this then. To specify this map, that is +3 as a column, right? +1, -1, and -3. Then m is going to be a length of this map, and here we can subtract these u and find the squares. So that is the distances between received equalized symbol and all the possible symbols from our constellation, right? Now we need to find the minimum of these distances. Even more so, we are not really interested in the minimum value itself. Rather than that, we want to know where is this minimum located. So we only specify the idx as variable of interest here. Tilde means that this is not going to be saved in any variable. This is going to be skipped, which is fine by us. So we find the index of the minimum distance, and accordingly yn is then going to be a map of this index. So this way we have performed this detection. Yes, so I might actually make this like this, a little bit shorter in vertical sense. Yes, so now we have these outputs generated. However, yes, what we want now to happen is not simply the answer, but also this entire algorithm that we are then going to make a decision what it was actually symbol, which we already did, yes, and send it to the output. Then we want to calculate the error and using least mean squares to update these filters coefficients. And let us do that. So the next step for us is to find error of equalization. Yes, so the error of equalization is, according to this diagram, yes, the decision minus the output y. No, sorry, not y, but equalize symbol and y. So here we have, well, we might actually name them as is in this diagram. So this is yd, and this is just y. Yes, so this eq symbol is going to be, well, I'm just going to add comment because I do like eq symbol more because it's telling more. I don't like this y, yes, because it's confusing in the diagram. This is particularly yd. Now it's everything clear. I only need to make sure it's also here mentioned as yd. So now I need to subtract this yd and this equalize symbol, and that is going to be error value. So error is going to be yd n minus minus equalize symbol n. Now that we have this error, we can apply this error for this algorithm, and here we need to know some step. Okay, so initially let us specify this as a variable step size of particular value, let us say 0.1. I'm not sure what it should be. Of course, I already did this and I know the correct value, but I want to show you how should we achieve that value, how should we know what is correct value, yes? So then once we have this error, once we have this step size, the filter coefficients, which are initially, well, almost zero except for the central type of this filter, we now want to update this filter coefficients according to the LMS method. Yes, LMS method, least mean squares. So without much typing, yes, I'm going to copy this line and explain it as it goes. So I'm going to update forward feed coefficients by adding to existing forward feed coefficients the error multiplied by the state that is now, as you can see, has been shifted by one position and filled in by new incoming symbol, so it updated at the beginning of this iteration, and by step size. So since this state is a column of LFF elements, this is also a column of LFF elements, so here we add up together matrices without much problems. Now I'm going to copy this line and repeat the same procedure for feedback filter. Feedback filter, and accordingly here we are going to use a state feedback. We didn't update the state feedback just yet because it is the last operation that we need to do inside of this function. So let us do that as well. After we have used this old value of feedback filter state, yes, we can update the state in the very same way as we did here. So here we have feedback, feedback, feedback. However, the new symbol being pushed in this feedback how it's called, register or state or memory, yes, whatever else it may be called, yes, we are sending the symbol yd, not x, yes. So we need to replace this by yd. So detected symbol, right? Now it's going to operate in a loop and find the best solution, hopefully, for us. Finally, I want to terminate that line of dots because, as you may have seen, it's not entering new line and continuous typing next commands, and it looks ugly. Yes, I just don't want it to look ugly, and that's it. And for that reason I add a new line at the end here. So okay, our function seems to be done, yes, and now we may try to run it and see how it goes. So we did something. Let us now see what is our output y. Our output y, surprisingly is 3, and that's it. I don't think that was our input data x-chan, right? As you can see, or not x but a. As you can see, a data was different, yes? And if we try to count the number of errors, a not equal to y, we will see that actually some of them are correct, but mostly it didn't do any prediction at all. It simply states it's 3, and since we have 25% occurrence of each of the symbols, yes, and it would have an accuracy of 25% automatically, yes, 2500 symbols were guessed correctly, they matched, just because they all were +3. Of course, this is not any good for us, and we need to do something to improve. Mainly, that would be this step size. However, simply changing this step size blindly to any number would have been quite tedious and long procedure. What we want to do is to get some intelligent guess as to should we increase it, should we decrease it, what's the problem with this value, yes? For this, what we actually are interested to know are these coefficients, yes? So I'm going to add a history for these coefficients as a variable inside of this function. So which is going to be initialized as n rows, and each row contains columns for each of these coefficients. Yes, so basically each row is going to have all our coefficients as a history, which we then will be able to plot in a picture and see what's happening with that. Naturally, what we want to do here is to actually output that as well. Coef history. Yes. So in case you don't specify it and specify only y, it will not output any history. But we do want to have this history, so that would be coef hist. It doesn't matter if I write it somehow differently here. Yes, this name of variable has nothing to do with this name of variable. This is built-in function, and it's important that inside of this function it's the same. Now we actually do need to record these coefficients into this array, because right now it's empty with zeros. Yes, so I copy this part, I say that nth row, which changes over time, yes, should be assigned this entire merge concatenated array of these coefficients followed by these coefficients. That is one column, right? So let's see, HFF, we don't know that. Well, we are going to need them anyway, because okay, we have made some equalizing, but what should we do? Well, okay, let's not hurry. Let's leave it as it is. Run our test scenario once more. So that would be line 17. I think I made some mistype. Coef hist. Coef hist. And then I here mistyped coef hist. So we run this, we can't run function, we run this script, it runs successfully, started a new line. Now I can say plot coef hist, and I will see how these coefficients change. So it says data value is greater than float capacity. That doesn't seem nice. What that means probably is that they are infinities. Yes, so let's simply try to type them out, not a number, as you can see. Meaning that our solution wasn't found because the step was too big. Yes, so more details about this again can be read somewhere here. Yes, this is about convergence, divergence, so we currently diverge from the solution. So that for us that means that we need to decrease the step size. Let's decrease it by 10 also let's add this command here, plot cohest, so that we don't have to type it each time. Grid on x label. That would be sample number, and y label would be filter coefficients. That would be actually subplot 2, 1, 2, because we are going to need a correlation function later on, and it would be fit in very nicely in this single picture, figure 1. So this way now we have a way to adapt these coefficients. Now you can see something happens here. Each line is one of these coefficients, which are 21 for feed-forward network and 3 for feedback network. They don't seem to be converging, yes, so we continue to change these. So let's change it one more decade. Run it again. Now it's becoming better. As you can see, somewhere around here it's starting to show promise of some convergence. Yes, again, that only means we need to continue decreasing this step. I can't run the function, so now this actually looks like some kind of convergence occurred around 6,000, yes, symbols. That is the delay of our symbol. What we want to know now, did that change our y's? Yes, as you can see now, it is -3, +1, -3, and so on. Let us check the final values of the y. That would be end -10 to end, and compare them one by one with the original values, end -10 and here. So they don't match. Yes, there can be multiple reasons for that. First of all, maybe our step is still not good enough. Second, the filter can introduce a delay. Yes, so we need some way to finding this. We could have, of course, printed out them column by column, then spend some time seeking similarities and finding how it is shifted by what position. So let's maybe try to do that right now. Here, can I find some resemblance here? Probably two small numbers. Yes, let's take 50 and 50. So do we see anywhere this kind of sequence above? Yes, -3, -3, 3. So -3, -3. No. Then again, maybe we can see this occurrence somewhere above, because this shift can be in different direction, in this direction or in that direction, and we don't even know what direction is our shift. So we have two -1s and then followed by 3. Well, I also cannot seem to find this one. This is not a simple thing. Much easier would be to implement some function that will do this task for us. Yes, so this is called a correlation function. So the correlation in MATLAB or Octave for that matter can be calculated by using a function called xcor. Yes, you however need to load package signal for that, so not problem for me. Signal in Octave, they are all free, no problems, and then we can call this function. Yes, you need to specify two sequences that you want to search similarities, and accordingly it will produce outputs as the values of correlation functions and the time shifts at which this has been calculated. So let us calculate this cross correlation function. Calculate cross correlation, in the hope that we can actually this way find this delay, where at which time shift these two sequences would start matching at least partially, right? So we are going to need values and the lag values as well. Yes, X core for the Y, which is received sequence, and A, which is original sequence. Yes, and we want to particularly use a unbiased correlation function. Yes, because values will be simply smaller, normalized in a sense. Yes, so it would be more convenient for us. Yes, so if we run this function, then we can make a subplot. So this one would be 2 1 1. I made a little bit mistake here. Well, not really mistake, it only changes the order of plots. We want to see this as a stem. X-axis is lag, y-axis is val. So X label time shift, Y label cross correlation. So I'm going to copy these labels too. Now if we run it, it should produce the correlation function. Here now you can try to zoom and locate the time shift. And as you can see, the maximum is not located at 0. That means we do have some time shift between these two sequences, which is 9 positions in my particular case. Yes, so meaning that again, if I try to study these sequences, now the maximum shift between them should be 9 symbols. So that would be these 3 symbols, these 3 symbols, these 3 symbols. So 3, 3, and 3. So somewhere in the 9 positions range we can find this. We may find, because it's not really guaranteed, but the correlation function was actually able to do so. But I believe honestly that the plus 9 means vice versa, that we will be able to find these somewhere below. Yes, somewhere below, -1, -3. Well, at any rate, this is not interesting thing to do. Much better would be to now introduce this delay here. Yes, to compensate for it. Yes, so we are going to compensate for that delay by, so for Y we are going to start from the first symbol. Yes, no, wait a minute, and train. So from delay, which is 9 in my case. Yes, so I'm going to simply use a 9 until the end. That would be my Y1, and also A1 is going to be A from 1 to end -9, like this. So now if I try to put them nearby, one under another, I still don't get the good results. Yes, somewhere they do match, as you can see here, somewhere they don't. But honestly, right now I get the impression that it's still the fault of our step. So let's continue changing the step. Now we are close to the solution, so let's maybe make it a smaller gradation. Yes, like this. Let's run it once more. Also, this doesn't seem to be nice, so let us actually change the limits of x-axis for this plot. Like this, xlim from -100 to +100. I don't think this delay is going to be any more. Yes. So since we didn't introduce that delay before calculating this autocorrelation function, this hasn't been compensated for. So okay. Well, okay, let us then introduce this delay here. Yes, so that would be y equal to so delay. So no, let us even do it like programmatically. Yes, so now we have this cross correlation function, and we can find the maximum value of this cross correlation function. Yes, so I believe it should point. But no, it is okay. Yes, so maximum that would be val, and we are interested to know lag at this IDX. No. I see. So if you have noticed when we plotted this picture, so I'm going to run it once more. Run selection. We had these here on the side, which is greater. So as a maximum, it has found this value. So we are going to actually need to intentionally make it shorter. Well, I don't think it's necessary to hustle. It's probably easier to say at the beginning of the program, because we either way will need it somewhere at the beginning, that our delay should be 9 symbols, right? Then here, once we have calculated this y, we can introduce that delay and delay up to end, and accordingly for y, for original symbols a, we introduce it as follows: 1 to end minus end delay. Now, if we calculate this correlation function, it should show that this delay disappeared, yes, and the correlation will be at maximum at 0, and also maybe we will be able to see sorry, incorrect variable name. Maybe we will be even able to see that in the command line. So scale must be known. Something happened. Something terrible happened. Why is that? Xcore unbiased. So let's check A. Let's we can actually check the size here. A and Y. They are different size. We have one extra Y. Yes, so we need to actually extract one of this, subtract one of the values. Yes, here. So Y is by 1 longer, or alternatively, probably we need to add here +1. Yes? No, as we can see, the delay isn't really compensated yet. Now it shows that we need +1. So I'm going to increase it to 10. This delay could have changed because we changed the step. Yes? Now you can see that maximum of cross correlation function is somewhere here. Also, let us then try to display last 100 values, last 50 values for each of these, yes, to see if they match better. Well, they still don't really match well, and now I'm a little bit confused that I might have forgotten something. But maybe we have already, how you can say, you can see from these that convergence happens too slowly. Yes, so probably we should start increasing this already again. Yes, so this is a search for this value.
Mic off, mic on.
So my apologies, and for some time I have been struggling with this fragment, so I have shortened it a little bit from the video and merged together with the second part. At any rate, for you it appeared hopefully seamlessly. And the problem here was that it didn't converge. It didn't converge no matter what kind of step I tried and so on. And that is reasonable and pretty simple to be explained. Yes, as you can see here, it takes some symbols, quite a lot of symbols, thousands of symbols, to actually get around the solution. However, before we get to this point, at this step we are going to have incorrect predictions at this decision device, and meaning these incorrect predictions with errors are going to continue to circulate. So each error is going to be reproduced multiple times in this entire system, which is not what we want. I was thinking that we are already at the final steps of these functions. However, it came to my attention just recently right now that we are still at the training step. Yes, for that reason there is the switch that during the training procedure we must disconnect this decision device so that it would not introduce any errors in this loop. Instead, we should produce already familiar and precisely known values as a reference, which can be used by this adaptive algorithm to improve these weights without suffering from this incorrectness. It still would produce some errors during the convergence time, during this period when the coefficients are going to slowly achieve their specific values. However, these errors will not be fatal. These errors will not continue to make situation worse. They will just be used to improve the coefficients. Yes. So what we should do now is introduce the training sequence. Yes. So as a training sequence, well, basically we should repeat this procedure what we have done here twice. First time for the training sequence, which should be specified for this function, already known, and second time for the um, real data, which may be noisy and whatever else, yes, without this reference of the training sequence. So we need to actually have here y training to be able to make correct convergence. Yes, so that means necessarily we have to introduce this at this side of the function as well, and here we are going to specify our a parameter. Yes, so this sequence of the transmitted symbols without interference, without noise, without any ideal perfect symbols. So we are going to end up in specifying the number of training sequences that we would like to use, yes? But right now let us use all available that we have, all the 10,000s of the symbols, yes? So the difference here is now that we have to disconnect this switch from the YD position to this training sequence, yes? So effectively in the algorithm that would change the expression of error calculation. Nothing actually more, yes? So that would be like this, yes? We are still calculating the outputs of the filter, we are still giving them as a function result, however they are no longer dependent on this, well, not this, at least not directly dependent on these errors that may have happened inside them. So now we are going to use specifically the training sequence for this process, and let's see if the situation actually improves. So I have meanwhile disabled delay, so let me return it. Now you can see that the convergence actually happened a lot faster, and the number of errors is still quite high. However, this number of errors is now caused by the delay. You can see that time shift lag is not at maximum value is not at 0, but rather than that it's at -10. -10 means that I need to decrease my delay by 10 positions so that it should be 0. Yes. Now I'm not sure if I explained here we should start with 1 plus delay instead of ending here with delay plus 1. Yes, so this goes away and here plus 1 is added. This is necessary to actually well difficult to explain, but otherwise they would not match each other, yes, correctly. So if we run it now without delay, delay is 0, convergence achieved here, and we only have 345 errors which have happened during this training procedure, yes. So basically all of this is training procedure, but now we can see that actually it would suffice if we send only 2000 of training symbols. So we should specify the number n training as the 2000s in this particular example, yes, and send it to this function, so that training doesn't necessarily take longer than it's necessary, yes. So we add argument here as well, and here for this we use only up to n train, right. We also need to use equalize symbols up to n train, and yd, which we may by the way call yd for train, also of this length. So we are going to return yd and yd for train, yes, and for this y train, accordingly it's going to automatically limit by this number when it reads here. So it should complete the training procedure in, well, in our case, in 2000 of these samples. Let's double check if it's true. Something happened here. It was because of the correlation function, by the way, that we needed to address these delays. And yes, right now you can see that y is 2000, a is 10,000. So we need to actually specify here not and but n train. Also you can see here that once the training procedure completed, nothing else happened. Yes, all the remaining values have been assigned as zeros. By the way, we might as well change that so it is not so. We're not really interested to store all these zeros, so here we specify also n train. Yes, so test scenario, we save it and run it once more. Yes, so 403 errors have happened in these first 500 symbols, most probably. Yes, we can check that. So the only thing we need to do is to save this as some kind of error vector. Then we specify n as a 1 to length of this error vector. And what we want to know is what values of n are at the positions of error vectors, where error vectors is 1. Yes, so if we run this, you can see, well, actually we end up with errors up to 1032. So that means that ideally, well, you need to realize that it's actually a random process. Because our data is random, it's every time you run this script is going to be slightly different, yes, but more or less it seems like a quite stable that we need to have at least 1000 of these samples not to be affected by training, yes, because afterwards errors disappear. That means the training process is successfully done. We have taken with a reserve, we have taken 2000, yes, so everything is fine. And now we can go to the actual equalizing, yes, of this channel. Now we have a state equalizer coefficients at some initial values that can be further improved after switching the switch to the decision device from training. Yes, in our function this effectively means that we are going to copy all of these, say here that now we have decision driven equalizing, paste it here, and that was accordingly training sequence driven equalizing, right? So basically this was a training process. Again, we will need to pre-allocate these variables. We don't need to initialize filters memory state. We don't need to set to zeros our impulse response, our states, because the idea of the training was to get them as some values which we may further use as already prepared good conditions, right? So that is very important, not to nullify all that we have achieved here. Yes, by the way, here I can see a mistake. I believe this should be no, it is correct. It is or not. Wait a minute, let's check the diagram. So for this diagram we should send here training. Okay, that is a mistake. So let's double check if it affects anything. Well, it does, and it does affect a lot. As you can see now here we only have 5 errors at the very beginning, and that's it. Our training has happened quite fast, so we may even increase this number. Probably it is reliable. Let's double check it. Well, no, it's better to leave it as it was, as this produced some divergence. So about optimum for this training process would be step size 0.01, but that doesn't necessarily mean this will be a good step size for the equalizing itself. So this equalizing is going to happen for all of the n symbols. Yes, so basically this way we compensate for that part we have spent some time on training and possible errors, and accordingly now we are going to start with clean state. And yes, as I say, I should have pre-allocated these vectors before starting. So basically for some reason it's indented. Let me try unident this, format unident section, right, like here. This also is for some reason indented. I don't want that to happen. And I'm going to move them under this command for better, how we can say, formatting or what else. So here we have saved coefficients for training. Here we'll save the coefficients of history of coefficients for the actual equalizing. Yes, so I'm going to add index E here, and later on I'm going to merge them together into one big array that will be saved as the output. Here I'm changing to n. I no longer need YD train, I need simple YD. Yes, now I need to return to the correct error expression when I have actually received signal from the decision device, yes, which is demodulator in our case, and here as well YD, which is already as it should be, yes. So here coefficients history saved in this array, and finally I'm going to merge them together into one big array vertically. So that would be like this, which is going to be output by this function, yes. So YD, also I want to output Y. But this it's called YD train here, and I didn't even use it here. Yes, YD train. So here we send not YD but simple Y train, yes, according to this diagram. Once again, training sequence not from the decision device but from the training sequence. In the first half of the algorithm, the second half, it's a decision device result, yes, YD. So we are going to say YD train as well. And I believe that should be about it for this function. Let us run it. Y and Y, I don't know, Y train we already no, in this script we don't have Y train. Yes, okay, so we can save it as Y train. So here we are interested to study, well, maybe both of them. Let's study at the beginning Y, then Y train, yes, and if we study Y, then we need here to have not N train but N. So now you can see that this actually took some time, and there is only one single error of our equalization process, yes. So the data has been equalized without noise and without any problems. Let us now change to the noise, yes. So let's now introduce some noise, 20 decibel for example, and let's see what happens with number of errors. Number of errors is 0, yes. For this, now we have a noisy signal. We use a noisy signal to train the equalizer, yes, so we do use noisy signal with this particular noise. However, for the reference we provide the training sequence, yes, which are perfect reconstructed symbol what the equalizer should receive, yes. So this way it adapts quite fast. Probably we can actually study how fast that is by specifying here that what we want to study is, well, actually, since our delay, well, no, let's better make it like this, um, commented versions, yes, like this. Y train 1 plus n delay, and a is going to be a from 1 to n train minus n delay. So we are going to comment either one of them whenever we want to get. So for example, now I want to study pictures for the training part. Yes, so you can see that somewhere around here at 2000 convergence happened. Well, it happened quite faster, but at 2000 we have switched from training to actual equalizing, and here some process started to happen. Still, as you can see, the equalizer returned to the same solution, and this is the number of errors that have happened during the training process, because right now we have also noise, yes, and this noise actually makes it slower to train. So let us try, I don't know, 15 decibel. Yes. So again, here as you can see, this equalizer coefficients actually work correctly, everything is fine, but what we want to see now is the number of errors for actually real data. Yes. Now we don't want to see error positions anymore, because as we decrease signal to noise ratio, there will be more and more of these errors, which is not what we want to see. So only 11 errors for 15 decibels. For 10 decibels, which is the lower bound of our signal to noise ratio range, we will get also 0 errors. Yes, so the equalizing with noise for this number of symbols, yes, 1 power of 4, actually performs quite good. Yes. So what we want to do now is to put that function in our code, yes. However, I'm still a little bit confused whether it works correctly. Ah, but wait a minute. Wait a minute. Yes, I do change SNR, however, that SNR doesn't affect anything. So that's why we get the same results, yes? Be that 0, minus whatever, we never really calculate the noise, yes? So for that reason, we actually need to now calculate this noise, introduce that, yes, and accordingly add. So let us do this part. I have not done it yet, so that would be done after the filtering on channel. Yes, here absolute values of the X-chan. That would be power. Well, I believe it is fine to well, okay, at any rate, let's specify this as log 2 of M. Yes, as a bit energy also. Convert decibel into linear scale. So noise power spectral density, and finally the noise generation process itself. So we generate the random normal distribution with standard deviation of and 0 divided by 2 and multiply the standard deviation to the process. Yes, so that is noisy signal, and our X-chan signal, which I believe we may now call more realistically as Rx received, would be X-chan plus S noise. Here we then specify X Rx. Yes. Now this is a noisy version of the signal. Yes, so again, let us return to 100 decibel just to see that everything still works correctly. We now calculate the error number for the actual data that was received, not training data, but the real data, yes. So this seems to be working. It does some mistakes, yes. Sometimes not, depending on the solution. Maybe it could be improved by this step size, maybe by this number of coefficients. It's up to you to try and evaluate if something can be done about this, but what we want to study now is the signal to noise ratio effect. So now errors should appear, well, maybe not at 20 decibel, because 20 decibel is quite strong signal, but as we go lower and lower, more and more errors should appear, just as any regular modulation type or whatever else. Yes, so still no errors. Something again went incorrectly. No, there are errors, and a lot. So it just happened that at 15 decibel it performed quite well. Yes, so here you can see that now at low signal to noise power this actually made worse. Yes, so as before we used 2000 symbols for training. That is when everything was improving, but once we switched to decision, yes, this decision with error started to degrade our filter, and accordingly we have half of the symbols with errors. Yes, so that's poor result. However, as we already know from the lecture part, yes, not really lecture part, but theoretical background at the beginning of this video, this equalizer particularly is very good at strong signal to noise ratio. That was mentioned. Suitable design for a system operating at high SNR. But even at high SNR it still cannot compensate specific types. At the low signal to noise ratio, yes, there is an effect of error propagation. So yes, and these errors are basically fed back in this feedback filter, yes, again at the input of this equalizer, and they circulate endlessly, yes, and add up more and more and more. So what we need to do now is to return to this program here and apply this function for the data we have simulated for different range of signal to noise ratio. Yes, so accordingly, well, actually, I believe, let me double check if I can make it a little bit smoother. We can. Let's make it so in this function where we output these dots, before outputting the dots, let us say this is fprintf training. Oh, sorry, this is equalizing already. Equalizing. And this would be training. It's just some smoothness, yes, of the output. Not really necessarily, but I like to do that in my programs. So, okay, now that we have it here, what we need to do, and pay attention that actually our function doesn't even tell us what are these filter coefficients, these and these. We don't even care about it. This program at once gives you the equalized signal, so it performs equalization as well. Normally, here for example, yes, in MSE algorithm, yes, we would have to calculate this filter, impulse response, one real part, imaginary part, apply this, form a complex signal, apply a delay, yes, so everything of that, except maybe for making a complex signal, will happen inside this function at once. So we really have a little bit here to do. So processing MSE equalizer, real part here needs to be added, and imaginary part. So we are going to copy this function, right? We are not even interested in this history or training, we are only interested in the actual output. That would be how was I calling it? Let me double check. Data RX real, so that it is a little bit different from previous data, so I don't lose it. Data RX real. Yes, here we should specify our real part of signal Rx, also a real part of the symbols A, the length of the filter on the feed forward, the length of the filter on the feedback, and number of training samples. So this parameter also needs to be specified. Let me remove that away. Add these section of the DFE equalizer, and train would be, well, let's use the same 2000 at the beginning. We'll see if we need to improve that, yes, but honestly it looks so far that it should be fine. So this produces us the real part. Same thing needs to be done for the imaginary part. Here, imaginary here, imaginary here. So this is actually apply equalizer already, yes. Already we have applied equalizer. Next step, we need to form the data Rx from the complex components, real part plus imaginary part multiplied by 1i. Then apply a delay, yes, which could have been actually done inside of this function, but well, maybe better to give us more control. For this reason, we need to set this delay here. This delay depends on your impulse response. So for one impulse response it might be 0, for another it might be some other number. So I have intentionally shown you how can you estimate what kind of delay is needed by using this cross correlation function, yes. So in case you try some, I don't know, different impulse response, yes, we'll see maybe there will be necessary some delay, or if you change these parameters it also may lead to some more delay. Yes, so but in this particular case the delay is 0, so actually we don't even need to consider that at all, but it's still better to do so just for the universality of the program. Furthermore, it takes just a few rows. Yes, and that is being done here. Yes, so we apply this delay to data Rx, yes, and we also form a data Tx transmitted, yes, from the symbol data from 1 to n minus n delay, DFE. By the way, let us call similar as, for example, there is delay Viterbi, delay DFE, delay MSE. Yes, so let's be consistent in names of the variables, DFE, and without this underscore line. Yes, so this way they will look the same for each algorithm. So we added these delays, and final step would be to calculate bit error ratio. Again, I'm simply going to copy this part because we already did that multiple times for Viterbi, for MSE. Now for these, we only need to make sure that you actually demodulate data Rx, not some other vector, and that you save the result in the DFE variable. So with that in mind, we can now add final plot. I'm going to make it in green color and change to DFE. Also, not a bad idea to add a legend. So the first one was Viterbi, next one was MSE, minimum mean square error. Well, actually it is called MMSE, yeah, but MSE is also recognizable. Next would be decision feedback equalizer, and finally would be a theory. So if we now try and run this program, I just want to make sure that it's some realistic number here. Well, let's maybe put to 4 so that it runs really fast, just to see if it works at all. So MSE equalizer, I believe it should have, okay, something happened as you can see. Yes, non-conformant arguments at the line 115. 115 is where we compare these, so bin Rx and bin data. Yes, here and here they have a different length. For y reason, and delay DFE and delay DFE. So if this delay is, oh, but wait a minute, we need to check data Rx and data Tx if they are the same first. Data Rx and data Tx, they are the same, yes, so at this step everything is correct. Now, sorry, here not SimK but data Tx. Yes, I didn't notice, I forgot to change. SimK was the delayed version for the MSE. It had its own other delay, not 0. Yes, so now this led to some mismatch. Also, I have noticed some not really bug, but unpleasant here, so I need to change this to DFE and add extra empty line for it to look smooth. Now this should produce these results. So imaginary part training, imaginary part equalizing, yes, everything is working. So let us wait for the final solution, because something is organized here a little bit differently than in my example, so this might actually produce somewhat other results. However, my previous results were looking like this, yes, for my impulse response here. These results are actually specified for the number of symbols 1 power multiplied by power 10 of 6, yeah, 10 to the power of 6, yes, 1 million symbols, not 10,000 symbols like right now simulated. And here you can see that it is clearly performing better than MSE equalizer. Clearly it is performing much worse than Viterbi algorithm, yes, and especially worse situation is at this low signal to noise ratio, as it should be according to the theoretical background, yes. It could go further below, however, my amount of simulated symbols was limited by this number. Yes, in order for me to get this line more smooth and further, I need to increase this number, which will take hours and maybe even weeks to simulate, which is not really feasible just for one picture. Yes, so let us see the results. Actually, it's working quite slow. I wonder if I have forgotten to change this. No, I haven't. Well, it is octave. In MATLAB it is working a little bit faster, so if it produces any unexpected results, I suppose I will have to switch right now to MATLAB to show you a little bit faster this. But I believe it should be fine because we already have tested this in test scenario. That is why it was important to make sure that actually it works, yes, and signal to noise ratio changes and errors occur, yes. So after you make sure that everything is working correctly, you simply change this to the 5, run the simulation, and get all the necessary pictures in your report. Don't forget that you need to add to the report also now a convergence plot for the coefficients and cross correlation function for delay estimation. Yes, not just one picture of these 3 lines. So this would conclude this practical exercise, which happened to be quite big, so I consider that it actually should count as a 2 practical exercises. Maybe in future I will even split it into the 2 parts, yes. So right now, for those of you who will complete this practical exercise, it will count as a double for your grade. For that reason, I believe it's not really necessary to organize any kind of exam or whatever. Well, yes, it works. However, it's very jaggy even for Viterbi because we have small number of trials. Yes, we need to increase this number to the power of 6. Yes, to get a smooth picture as is here. It's still even not so smooth at the power of 6 here. Yes, but at least it shows the total tendency. So this would conclude the practical exercise number 7 and 8 as it turns out now, yes, and please stay tuned for the practical exercise 9 final on the rake receiver. It will be uploaded very shortly. Thank you for attention. In case of any questions, please don't hesitate to ask.